All right, I think we're going to go ahead and get started. Welcome, everyone, and thank you for being here. My name is Cami Sacco, and I am a climate programs manager at Second Nature. And welcome to today's webinar, which is Geo-Exchange Systems: A Path to Decarbonization. So just a couple logistics. This is being recorded, and after we have the session, we will be sending out the link and we'll also have it uploaded to YouTube. If you have questions, please put them in the Q&A function and you can add them at any time. We also have the chat enabled, so if you have anything that comes up or any experiences that are related to the topic, please feel free to put those in the chat. We welcome a lively chat. And then you're on mute mode, and during the session, all attendees will be on mute except for the panelists. So just an FYI, some folks may know or may have seen, this is part of a full climate action planning webinar series, and this is the second part of the full 12 webinar series. So we are shifting back and forth between decarbonization tactics and then more process oriented around climate action planning. And so this is our first one focused on a decarbonization tactic, which our panelists will talk a little bit more about that. And an FYI, for those who don't know, we have our 2025 Higher Education Climate Leadership coming up in Washington, D.C. from February 2nd to the 4th in 2025. And if you're interested in that, registration is open, as is the request for proposals or our call for content. And that call for content ends September 27th, and registration will be open through the end of the year and into January. We also have a working group. We have a couple working groups with Second Nature, and one of the opportunities we have for engagement is with our Intersectional Climate Action Leaders Working Group. And this is meant to be a BIPOC affinity space for members and non-members of the Climate Leadership Network. So if you're interested in this, you can scan the QR code or contact our colleague Blythe, who is leading that and would be happy to have you. And then before we get started, the last slide, we have a new IRA community of practice that we are launching soon. And so if you're interested in that, please scan the QR code and one of our team members will be in touch with you. So we wanted to start before we opened before I introduce you to the panelists, and we had a conversation about this. We just really wanted to understand where folks are in their journey around geo-exchange systems or geothermal systems. And so we just wanted to kind of gauge folks. So we're gonna launch this panel, and we'll have it open for about 2 minutes. And this will, again, just help our panelists to understand their audience and who they're talking to, and where people are at in their journey. So I'm gonna go ahead and open it. And then we'll keep it open for a couple minutes. Okay, so we have close to 90% of folks. I'm going to go ahead and end the poll. And we're going to share this with everybody. It's really, again, for us to get a good idea of who's in the room. And so you all know who's in the room too. We want to make sure that this information is accessible to folks. And so you see that we have about 25% said that geothermal systems tap into the Earth's core. 75% said they didn't, and that geothermal equals Geo-Exchange, and that was close to 50-50. And then are you familiar with how heat pumps work? And so we have a pretty mixed bag. And so our first panelist, Michael, is going to talk a little bit more about that. And so I want to then have our panelists come on camera, and I'll do just a short introduction. And then I'll hand it over to I'll hand it over to Michael. So we have Michael Ahern, who is with Evergreen Energy, and Michael's going to be talking a little bit, he's going to give us a little intro to Geo-Exchange systems and kind of what the term means and kind of some misconceptions, and then also about some of the larger work that Evergreen Energy has done with different institutions. And then we'll have Ted Mendoza, who is a capital project manager with UMass Amherst, and I think has been there for close to 20 years, and will have a little bit more information when I introduce him with his bio. And then Justin Owen, who is at Weber State University, which is in Utah. And so Justin will talk a little bit more about having a system that is up and running, how to maintain it, where they're going. And I'm really excited to have the three of them here. I want to note we had a fourth panelist planning on being here, Carolina Kudamis-Jones, who's with Smith College, and she had a family emergency and had to drop out. But I would highly suggest, if you're a woman and in the field, to find her on LinkedIn. She is really involved in some women in construction groups, and so she could possibly connect you, and you could get in touch with a network that is more women focused within the field. So we're going to start with our first panelist then, and this is Michael Ahern. So let me grab your bio real quick. Maybe I might not actually be able to see your bio because I'm sharing my screen. So Michael, why don't you go ahead and get started, and I'll do an introduction after you're done. So apologies about that.
Sounds good. Thanks, Cami. Thank you, everybody, for attending. If you could jump to the next slide, please. So it appears as if the bulk of the folks on this session did understand a bit of the distinction between geothermal and geo-exchange. Geo-exchange is really when the Earth's or some source is being used, whether it's the Earth, and I'll talk about a couple of different opportunities that we're seeing on projects around the country, where you have a low-grade energy source that you use both for heat in heating season and as a heat sink in cooling season, to combine with water source heat pumps to temper those spaces and to provide comfort, as opposed to some projects around the country right now where they are going much deeper into the earth for purposes of strictly heating the buildings, using high level of heat and deep in the earth's core to be able to provide heating to space. So what we're going to be talking about today primarily is around the geo-exchange side. In many circumstances around the country, when you talk with these projects or with people about these projects, geothermal and geo-exchange end up being synonymous for most lay people. And I think that that's okay, generally speaking. But if you do want to get a little more technical and in a little bit greater detail, I think it is valuable to use the geo-exchange term when talking about water source heat pumps and providing both a heating and cooling solution to spaces. Go to the next slide, please. So just to talk through a few different types of projects that are occurring around the country right now, we have several projects on the East Coast in New York and in Ohio, where we are seeing traditional closed loop geo-exchange projects, and that's where you're running tubes down into the ground, typically somewhere between 600 and 900 feet deep. and you have a very large closed loop well field that again is taking heat out of the ground in the winter and putting that heat back into the ground in the summer. You have a heat transfer through the grout that's in each one of those wells, each one of those bores. And typically for a larger campus, you're going to see a fairly expansive well field. I'll be talking about one of those projects here in a little bit. Smith College is a circumstance that also implemented something along those lines in Massachusetts. And again, we have a project in early development, design and development right now in New York. But we're seeing these types of projects around the country, a couple on the East Coast, as I just mentioned. On the left-hand side of the screen, closed loop ground heat exchange is a technology that is emerging. There's several players in this realm where they're actually submersing heat exchangers into the aquifers, still running a closed loop piping system going down into the heat exchanger and then coming back up. But if this technology emerges as expected, it's a much more efficient means of transferring energy from the aquifer up to buildings and then back into the aquifer water in the winter or in the summer, and that can become or require a much smaller footprint than does a traditional closed loop geothermal bore field. And we're seeing several of those being developed in the upper Midwest at the moment. An open loop geo-exchange is a little bit different, somewhat similar to what I just talked about with the ground loop heat exchange solution. And we have 6 of these types of projects that are in design, development, or construction, primarily in the upper Midwest right now. And that's a circumstance where you are bidirectionally moving aquifer water out of the ground across a heat exchanger and then back into the aquifer, never introducing it to the open air, the aquifer water, or to any contaminants, so that integrity of the aquifer water is maintained. But essentially, you're taking water or taking heat out of the buildings in the summer and transferring it into that aquifer water, storing that heat in the aquifer, and then in the winter, you switch the directional flow of that aquifer water and you take the heat out of the hot water zones and discharge it into the buildings. And then in the summer, you're taking the heat out of the buildings and putting it in the aquifer water. And again, we have several projects under construction and design in the upper Midwest, and actually primarily in Minnesota right now for that type of technology. A project that it's a system that's operational that we operate and maintain out in San Francisco is Mission Rock Utilities. It's a business we formed back in 2016 to serve a new development that's adjacent to Oracle Park, where the San Francisco Giants play. That's a system that's actually going to use, at full build out, use the energy from San Francisco Bay as our primary means of both heating and cooling roughly 3.5 million square feet of development on what was previously a surface parking lot. So again, that's the phase 1 of that system is already built out, which includes the redundant energy solutions for heating and cooling purposes. At full build out of the campus, we will be pulling bay water out from underneath the Pier 48 there, running it through a heat exchanger, and then using that tempered water loop, roughly 55-degree water, to heat buildings in the heating season and cool buildings in the cooling season with water source heat pumps. Another example of Geo-Exchange, just using a different heat sink rather than the ground or aquifer water, using the San Francisco Bay water. And then the last example, talking through, and again, this is a technology that's been deployed worldwide for decades. 2 systems that we operate and manage in Minnesota, one up in northern Minnesota and one in the Twin Cities in St. Paul, are adjacent to primary wastewater treatment facilities for those 2 urban centers. And we are designing and developing solutions where we would take the effluent off the wastewater treatment facility before it gets discharged back into the river, or in the Duluth example, back into Lake Superior. And we would pull the heat off of that energy source using then water source heat pumps at our energy center to boost the temperature and be able to serve the square footage in those 2 downtown districts. Just another example of Geo-Exchange. There's a system like this right now in National Western Center in Denver. And the largest of these systems worldwide is under design and construction right now up in Markham, Ontario. So this is a technology that is continuing to grow within the energy industry. So the one closed loop Geo-Exchange project that I want to touch on a little greater detail is a system that we are in the process of commissioning. We've just gone through 4 years of construction to decarbonize Oberlin College's campus. It's a liberal arts college in northeastern Ohio, just southwest of Cleveland. They made a commitment to achieve carbon neutrality by 2025, and we are very close to achieving that goal for them. Go to the next slide. So as I noted, they had a commitment to achieve carbon neutrality by 2025 as compared to their 2007 baseline. There also was a strong guidance from their leadership to make sure we did so in a manner that was cost compelling for the college, and ultimately stayed with the core mission of the institution around education. So as we implemented this program, we spent quite a bit of our efforts toward integrating it with the curriculum of the institution, and also obviously always with an eye toward being cost conscious. Next slide. So in 2020, there was a call to action just because of an antiquated steam system on the campus. They also, the Geo-Exchange solution became viable because of the fact that the campus and the college was looking to expand their cooling needs, much more summer programming now than they had even back in 2020, pre-COVID. And then the overall program, the Sustainable Infrastructure Program, continued to expand as we were in planning and design activities because of some other infrastructure needs around electrical and fiber and their fire protection systems and their control systems. And so we took what was a carbon neutrality program and turned it into a much more broad sustainable infrastructure program. So broadly speaking, we installed 850 vertical closed loop Geo-Exchange bores up on the northern side of campus. We had entirely replaced all of their heating and cooling infrastructure throughout the entire campus. We worked in roughly 55 buildings where we upgraded all of their HVAC infrastructure and controls and electrical infrastructure inside those buildings to convert them from steam to low temperature hot water, but also to upgrade systems that had deferred maintenance and were in some significant need of rehabilitation and renovation. We were able to address all of those challenges as we worked across the campus and implemented this overall program. The Geo-Exchange system itself, we started construction of that in May of 2023, and we have just wrapped up the bore field installation. We're restoring what was and will be the intramural practice fields, which is where the Geo-Exchange system is. Again, I noted we dug or drilled 600 feet deep on 850 wells, and we left some space and accommodation to grow that well field, that bore field, if it ever becomes necessary. Overall, from an implementation perspective, we needed to make sure we addressed what was the most at-risk infrastructure, which happened to be in the southern half of the campus. So we really started at 6 o'clock on the clock down on the south side of campus and worked our way around clockwise from the south to the west to the north and then to the east over a 4-year construction program. So dark blue in 2021, aqua colored blue in 22, both building work and distribution. The buildings in green and the piping in green up on the north in 23, and then this year in 24, we're finishing out on the east side of campus, what you see in gold. As we are doing all the building renovations and installing all of the new distribution system, we're also working in the central plant initially to make sure we were simultaneously able to send hot water and chilled water down to the new buildings on the south side while still sending steam to the buildings that hadn't been renovated yet. And then just systematically decommissioning portions of the steam system as we were able to put new hot water and chilled water pipe in. And then once more simultaneously, not only converting them to be able to be integrated with the Geo-Exchange well field, but also then addressing any other unknown infrastructure needs, known and unknown infrastructure needs inside those individual buildings. So we are fast approaching startup and commissioning of the overall bore field with the central plant with the new air source and ground source heat pumps. And we're also already seeing significant energy efficiency improvements. We're seeing roughly a 30% decrease in energy consumption on campus as a result of this renovation and this move to low temperature hot water instead of steam. And some significant water savings on campus, roughly 5 million gallons per year of water consumption reduction as a result of this overall program. We're on target to hit carbon neutrality by next year at the campus. And we're already working on additional opportunities for advancement to become carbon positive or carbon negative, I should say. And by adding in more solar PV on the north side of campus, and doing that will also actually enhance the resiliency of the campus and actually turn it into a bit more of a microgrid. So thank you, and we'll pass it along to Ted, I believe.
Yeah, thanks, Michael. And I do want to read your bio, and my apologies for that. So Michael has 30 years of experience in leading development, engineering, construction, operation, and management of industrial and energy systems. This includes operational oversight of businesses in the industrial and energy fields with a focus on district systems over the last 15 years. At Evergreen, he leads the development and advancement of mission-based campus and community energy and utility systems that achieve clients' strategic goals. He holds a BS in business finance and from the University of Notre Dame with an international business minor. So thank you again, Michael. And we'll circle back, Eric, with your question in the chat, and we will move on to Ted. So Ted Mendoza has been a capital project manager for UMass Amherst Design and Construction Management Department since 2012. He has over 30 years of experience in design and construction, and his balanced focus on energy efficiency, network technology, and mechanical systems bring a unique and practical perspective for a myriad of building and campus-wide system and infrastructure projects. His vast knowledge makes him uniquely qualified as a part of UMass Carbon Zero's leadership team. All right, take it away, Ted.
Right. Thank you, Kami. And thanks for having me. Can you go to the next slide, please? So just a few general stats about UMass Amherst. We were founded in 1863. We cover about 14,000 acres, 170 buildings plus, and about 12 million gross square feet of building space and growing. We have about 30,000 students, the majority of which just moved in this past weekend. 6,000 faculty and staff, and I'd say UMass Amherst would be considered a medium-sized higher ed institution, but I'll leave it up to others to confirm or deny that. Next slide. So at first, we needed to understand our current heating and cooling needs on campus. And what you see here is a profile of about a quarter of our buildings on campus. Heating trends up in the red and cooling trends down in the blue, which is a rough representation of all of our buildings on campus. We actually did a subsequent calculation for all of our buildings on campus, and the profile still held fairly true. So we're looking at about a 3-to-1 ratio of heating to cooling, and that's important to note as we get down in the presentation later on. Next slide. So back in around 2019, 2020, we embarked on this carbon mitigation study that asked at a very high level what it would take for us to operate as a carbon neutral campus. And what you see here is that we looked at a lot of different technologies. You can see the kind of layers of the cake there, not just the ones in red. But one of the lessons that was taken from this is that if we focused on ground source heat exchange coupled with heat pump technologies and low temperature hot water, that would take care of 2/3 of our overall greenhouse gas emissions footprint. So it's important to note that even though we're focusing on that, ground source heat exchange and low temp hot water technology, it's not covering 100% for us, right? So we know that going into it that we still need to look at some other things. You can see there in the green there, sorry, real quick, that for numbers wise, it equates to about 80,000 metric tons of CO2 emissions reductions. Next slide. So subsequent to the study in late 2021, we took the next step and completed a schematic design level analysis on about a quarter of campus. So the kind of southwest quadrant of campus, you could see some of the buildings highlighted in color there. And that included the installation and a thermal analysis of an 800-foot geothermal test well. So we can understand more specifically what size equipment we needed, what the infrastructure would look like, and what the overall installed cost and timeline to implement it would be. So fast forward to summer of 2022, and what we found, as you can see there underneath the tile there on the upper left, is that it would cost about roughly $500 million and about a 7-year timeline to implement the system, again, just for a quarter of campus. In addition, we learned that our largest open field that we had to establish our Geo-Exchange well field, which is highlighted in the dotted yellow circle there off to the west of our campus, that's our largest athletic field there, would really only support the 30 or so buildings that were identified in this proof of concepts study, that analysis that we did. So this kind of surprised us, actually, realizing that this, high level idea of promoting ground source heat exchange, heating and cooling throughout campus, it just simply wouldn't work throughout UMass, because we just simply don't have enough land, open land, to implement the wells and implement that technology. So we realized at this point that we needed to pivot and find other ways to decarbonize. But before we kind of went down all these other avenues, first we wanted to play out our ability to implement Geo-Exchange technology throughout campus. So as kind of the final parts of this phase 1 effort, we installed 4 other test wells. You can see in the 5 yellow stars there which ones we did and where they were on campus. And we analyzed the thermal properties at each location, so it would help inform our current and our future planning discussions if we were to look at converting a building or a series of buildings into ground source heating and cooling systems. Next slide. So in pivoting, what we're doing now is threefold, and I'm looking at the blue text here. We realize that number one, that ground source heating and cooling or air source heating and cooling systems for new building projects or major renovation construction projects, that still made sense, because there still is an investment in those buildings to put in new mechanical systems or do a major gut and replacement of mechanical systems. And that seems to be kind of the tipping point for us as far as converting buildings for the sake of decarbonization versus converting buildings because we wanted to refresh them as we normally would anyways. The second point is that we wanted to now shift and do some investigations at the end of our existing steam distribution and infrastructure to look at kind of pruning back the buildings that were at the end of the line and see if we can implement decarbonized systems there, and maybe even do it at a building level or maybe at a regional level. And then the third point is that we shifted some focus and more effort into exploring solutions at our steam source, right? So looking at our combined heating and power plant, which is on our west side of campus, and really looking at how can we turn the turbine other than burning fossil fuels, or how can we kind of supplement the system there using carbon neutral or carbon zero type of techniques. Whether they exist now or not, or they will in the future. So, really acknowledging, up to this point in our process, we're acknowledging and realizing that we have these current challenges because of the types of buildings we have, the size of our campus, and these are things that we're still kind of struggling with. So we want to invest time and resources to better understand how to overcome them. Moving up to the black text there. So, we acknowledge the not having enough land to meet Geo-Exchange or geothermal needs for heating and cooling. We also have this 3-to-1 essentially heating and cooling ratio. So even if we implemented Geo-Exchange, which is great in kind of a balanced heating and cooling scenario, we still need to supplement our heating needs by some other means during our winter season. Realizing also that by decarbonizing, we're essentially electrifying our campus. We needed to look at what are the limitations and where we would have to put some investments into our own campus electrical infrastructure, and in conjunction with our utility partner, which is Eversource, making sure that the utility grid that feeds our campus also is, meets to the challenge for us to go to full electrification in the future. And one of the last challenges we have is we have some buildings and some areas of buildings that we'll just need to keep some kind of steam just because there's no other technology that we know of that can displace what the processes are being used there. So like autoclaves, cage washes, we have steam that we use for dishwashers for our dining commons. Those are things that we'll need to maintain, and we need to look at, how we're going to do that. One of the other things too is with steam, it provides heat even during a loss of power on our campus. There are some buildings, a lot of buildings that are dormitories that people are living in, that if there were a loss of power and we converted to an electrified system, now we have to have some kind of a plan B in place. So that's something that we need to look at. Next slide. Oh, that was a nice transition there. So visually, our approach looks something like this, right? So we have the proof of concept, which is in the green rectangle there, dotted rectangle. So we did our study, we did our schematic design. We know how much it would cost, how long it would take. There's no appetite at this point from leadership to pursue that. $500 million for a campus of our size is a lot of money. And if that's for a quarter of campus, it's really a $2 billion investment in all of our campus. Also knowing that we're limited by the land for to put our geothermal wells. We do have, so shifting gears, we do have 2 new building construction projects underway, our computer science laboratories and sustainable engineering laboratories buildings. And we are applying a ground source heating and cooling system for that. It's a regional system that would expand out into potentially other surrounding buildings. So that's under full design now. It's expected to be completed in March 2026. It's going to start construction later on this year. And that's also a supplement to another project that we have that's in the vicinity, which is a thermal energy storage tank, which is going to be completed a little bit sooner, September 2025, which is going to be for cooling only at first, but then we're looking to see if we can convert that in the future to a cooling and heating energy storage tank. And then finally, over on the east side of campus there, Butterfield House, that was after we did this study kind of at the end of our steam line there. Our steam goes from west to east, generally speaking. And we've identified one of the buildings there as a dormitory and identified the air source heating and cooling system as the viable one that we would like to pursue. So we're now looking at getting funding from our trustees, and then we would move forward with that. Next slide. Well, really, our big swing, right? Our big swing at the fences will be if we can address decarbonization at the source, right? So where our steam heating is produced at our combined heating and power plant. So from this perspective, we're looking at a few options. We just finished a round of pilot testing for biofuels. And it looks like that's something that we'll be pursuing a little more aggressively. And we are monitoring and having conversations with startups around some of these other technologies that are still not necessarily mature enough for us to implement. So around hydrogen, micronuclear, and deep geothermal, that's the 1 to 2 mile deep option for tapping into the heat of the Earth's core. We're looking at supplementing some of our heating production through energy storage, concentrated solar thermal systems, wastewater heat recovery. I think those have been mentioned. And we're looking at electrifying some of our steam boilers, just as kind of a point there in the little asterisks in the red. For when we did our proof of concept study, we said, what if we just electrified all those steam boilers? How much electric load would that take? And just for the quarter of campus that we would need to support, it actually would double our campus electric load from 30 megawatts to about 60 megawatts. So now multiply that times the other 3/4 of campus, and we're looking at 120 megawatts of electrification on our campus. Next slide. So looping back to the beginning from the study, in parallel to all this work that we've accomplished up to this point, we've maintained this open dialogue with our campus stakeholders via this Carbon Zero Advisory Board and creating this campus-wide engagement so that we're keeping our stakeholders, and this is a blend of faculty, staff, students, we're keeping them all updated on kind of the challenges that we have, but also creating opportunities to open up to them. We realize that this decarbonization story is really kind of like watching our own movie unfold as it's still being written. So, you know, like you all, I can't wait to see how it all kind of works out and comes together in the end. That's it for me.
Thanks, Ted. All right, so our next panelist is Justin Owen with Weber State University. And Justin is the Interim Director of Operations at Weber State. During his tenure as the previous energy manager, Weber State University's already substantial energy savings have continued to grow, and WSU has continued to be cutting edge with the installation of ground source, variable refrigerant flow, and solar systems. Justin holds a master's degree in environmental science and public affairs from Indiana University and a bachelor's in geography from Weber State University. Justin is a certified energy manager, a certified educational facilities professional, a certified water operator, and recently completed a certificate in energy finance from Yale. You ready, Justin?
Oh, I'm ready.
All right, take it away.
We can go to the next slide. So just a little background on Weber State University. We are a public institution. This campus that you're looking down on in this picture was established in 1952. We've got about 26,000 students, about 1,500 full-time equivalent employees. We are a dual mission institution, so we fulfill the role of both a university and a community college. We're actually open admission. And we have a lot of first-generation students, a lot of non-trads. Most of our students actually commute to campus. We only have 1,000 beds on campus. And so we're kind of we're a small city that gets populated in the morning and then leaves in the afternoon. Total gross square feet, we're about 3 million. About 2.5 of that is on the main campus here. And we do have a number of satellite campuses as well. So we're located in Ogden, Utah. That's about 40 miles north of Salt Lake City. As you can see, this picture, we are located in the foothills of the Wasatch Mountains. In fact, if you look up towards the snow there at the top of the picture, the other side of that snow is the Snow Basin Ski Resort, where the Olympic downhill was held in 2002 and will be again in 2034. So we're looking forward to that. Climate-wise, we're 6A, 6B, cold winters, hot summers. We are a cooling-dominated campus. However, we design our systems for 0 degrees Fahrenheit. So there is this kind of, we might get up to 105 degrees and we might get down to 0. And that's kind of what we design for. We can go to the next slide now. So as far as our goal is concerned, we are a signee of the American College University President's Climate Commitment through Second Nature. Originally, our goal was 2050. As we've gone through the process of kind of nailing down what our approach is to that, we've moved our goal up to 2040. In terms of our legacy infrastructure, our buildings generally are VAV or multi-zone, utilizing hot water systems that are serviced by hot water and chilled water systems that are serviced by centralized heating and cooling. So we have a legacy steam boiler plant. And as I mentioned, that was initially built in the 50s. And we have a centralized cooling plant. So one of the questions that we came up with, particularly for us, was, how do you heat a campus in a climate-friendly way, right? Traditionally, we've done boilers. Do we look at cogen? Let's go to the next slide. And so the previous panelists have done an excellent job of explaining what Geo-Exchange is. I usually use the term ground source. Those two terms are kind of interchangeable. These are the options we looked at. Number one was just, what if we just offset all the natural gas we burn? It's about, traditionally, our baseline natural gas consumption is about 200,000 decatherms a year. What if we just offset that? We didn't really feel good about that approach, both from a financial perspective and from the other environmental effects of burning natural gas. Utah, if you're not familiar, the Wasatch Front, we get a temperature inversion here, and a lot of the pollutants just get socked into the valley. And so we wanted to kind of be a little more proactive in that realm as well. We did look at things like what if you hit heat with a resistance coil, right? Kind of the technology we're familiar with in a space heater. And we really moved into this world of heat pumps, right? So this picture is I can't remember what building this is, but this is a picture of some heat pumps on campus. Now, we use a specific technology called variable refrigerant flow, where basically, instead of using air to move energy through a building, right? That's kind of what we're used to. You actually circulate refrigerant throughout a building to recover heat or remove heat or add heat as needed. Now, these are all water source heat pumps, and we've connected them to our existing chilled water infrastructure, right? So we have the chilled water loop that our central plant uses is circulating water 24/7. That's the energy source for these heat pumps. Now, the other panelists have kind of talked about this already, but as these heat pumps inject heat into the space or remove heat from the space, the temperature of the central loop is going to change, right? Now, the nice thing about heat pumps is their tolerance for the temperature of water they need is really broad, right? So these particular heat pumps are good until about 47 degrees Fahrenheit, and we try to keep the loop at 50. But they can operate quite well with warmer water. So if my loop is 70 degrees, 80 degrees, 90 degrees, I don't really care much. But if I'm heating in the winter, I'm cooling that loop down, and eventually it gets so cold the heat pumps can't work. And that's where this idea of ground source comes in. Let's go to the next slide. So this has really already been explained, so I'm just going to touch very lightly on this. At Weber State, we've really used two different approaches to implement ground source fields onto our campus, because what we're trying to do is align our capital improvement, align our energy program, and align our capital development to get us to that 2040 goal. Because what we're trying to do is deploy ground source fields in a strategic way, whether they're centralized and networked with the entire campus or have the ability to be isolated to provide the heat. Now, one thing that I'll throw out here is campus is built on an old landslide. And so the depth that we can drill to is not quite as deep as what Michael mentioned. Our deepest wells are about 400 feet. And that's just an economic question. Once we hit that bedrock at 400 feet, it makes it easier to just drill another hole, right? But one idea I want to put out to this group is the effect of building efficiency. Having that come in parallel with your ground source development can be very powerful, right? If I'm decreasing the heating need the heat of a building by, let's say, 40%, right? That's going to decrease the investment needed in the centralized assets, which is therefore going to decrease my capital expenditure, right? And so what I'm really trying to do with campus here is build a system that has both the energy savings and the environmental benefit, as well as operational and maintenance savings. And it looks like I've got a question about VRF. I will address that as we go forward. So let's go to the next slide. So these are a few of the big questions that I think are important to think about when you're implementing these kind of systems. Now, at Weber State, our first air source heat pump building was in 2013. Our first water source was in 2014. And so we've been doing this for 10 years, and we've learned a lot of things through trial and error along the way. But some of the big questions that I think energy managers and sustainability professionals should think about are listed on this slide. So I teach an energy management course here at the university, and one of the things I try to drive home with my students is this idea of programs, not projects, right? We're trying to build something that is financially sustainable and will continue whether or not I'm in this seat or my boss is in his seat, right? So one is, where is the funding coming from? At Weber State, like I mentioned, we're aligning capital improvement dollars with capital development and our internal revolving loan fund to make these projects happen. Another one is, what happens to the energy savings on campus? At Weber State, we've built a model where if we save money on energy projects, that money gets invested in more energy projects, and that's that revolving fund. Who makes the decisions regarding capital improvement? I often see a disconnect between the operations and maintenance staff, who I represent, and the capital planning and construction staff, who I think Ted is more involved with. Connecting those groups, I think, is very important. And then from an engineering perspective, if you can diversify your connected load, right? Every building behaves a little bit differently in terms of the heating and cooling that it needs. And if you connect a building that's cooling to a building that's heating, they will actually exchange energy before you have to go to the deep earth. Okay, next slide. I'm hurrying, Cami. I saw your message. So a couple highlights, buildings that I'm proud of. One, our science lab. This is a 130,000 square foot building. It's half VRF and half heat recovery chillers with chilled beam. Its site EUI is 38. It's fully electrified, and it's been running for, oh goodness, time is flying. It's been running for about 7 years. Our social science building, this is the most efficient building on campus. Its site EUI is 23. It has its own ground source field that is underneath a rugby field. It can share energy with campus or call for energy from campus if it needs to. It's only done so once in the 6 years it's been operational. And then just recently, we completed our Norda engineering building there at the bottom. That's 140,000 square feet, and its site EUI is about 30. That's where I teach, and that building makes the energy nerd in me happy because all the infrastructure is exposed, and I can literally trace, from the centralized piping through the heat pumps along the refrigerant lines to the spaces. So currently, we're about a third of the way electrified. I think I neglected to mention our approach. Both Michael and Ted mentioned the idea of low temperature hot water. When I say low temperature condenser water, our loop is generally in the 50-degree range, and that's what's being sent to the heat pumps. I did see another question come through the chat about what to do when your heating and cooling loads aren't balanced. Our approach to that, one, is this idea of diversified building needs, right? One building might have a data center that's always going to give you heat. Another building, like a science lab, might have very high ventilation rates, so it might need some cooling. And those can balance, right? But the other idea I'll throw out to the group here is the idea of a hybrid system. So we do have backup heating and cooling for the campus loop. We have some condensing boilers that run during the winter if the ground source fields can't keep the loop warm enough. And then I have cooling towers if I ever need to shed some extra heat. So currently, at our current pace, we will fully electrify the campus by 2035. I'll try and do the next slide in like 30 seconds or less. I did see one question come through about the complexities of VRF. It certainly is a concern. I have a 3-page document on all of the lessons learned. Most of the problems can be solved through good commissioning and installation. However, we are moving to this world of hybrid VRF, where the only refrigerant in the system is between the heat pump and the branch controller. Everything else is water. And so the football stadium you see there at the right, we just completed in the past couple weeks, and that is hybrid VRF. Another project I'm excited about is our basketball arena. We will start construction on that to be fully electrified in December. And then as we continue to build districts, there's a lot of interesting implications with this kind of system. One of the things I'm going to do is one of my capital improvement or capital development projects finishes in May is isolate 5 or 6 buildings on campus to one geofield and see if I can warm the deep earth up over the course of a summer or multiple years, so I don't have to use those condensing boilers. We've got a master plan through 2035 to electrify the rest of campus. 4 or 5 more ground source fields should give us all the heating and cooling that we need. It kind of depends on how the campus grows. And I think that is my last slide, and I think we can go to questions.
Thank you all so much. That was extremely informative, and we definitely have quite a few questions. So let's, looks like most of you have answered them in the chat or in the Q&A. But let's go to, we had a couple questions in the chat. So Eric asked, how significant is the heat balance in a Geo-Exchange if heating is much greater than cooling in the design, and how much, or how is this addressed? So Justin, you answered that a little bit. And then if folks, need any more questions answered, if they weren't answered enough in the chat, then feel free to, or in the Q&A, then feel free to put that in the chat too. So does anybody want to go ahead, Michael?
Yeah, I would note, and Ted said the same, and as did Justin, it's tremendously important to have a design that has a balance between heating and cooling. And there's a number of different opportunities for doing so. You can integrate solar thermal, you can capture waste energy off of some other processes to try to put heat back into the ground if you are a heating dominant. At Oberlin, we also integrated existing assets from the central plant as an opportunity to balance the load and as well as to provide redundancy to the system in the event that there is a disruption. So we didn't abandon all of the existing generation infrastructure that the college had previously invested in. There's also, we're working with the local hospital that's adjacent to the campus at Oberlin, where we would take the heat from their condenser water system, from their cooling system, and actually you have our geothermal return be their heat rejection for the hospital. They're generating cooling at the hospital year round, and our geo pipes run right past the hospital. So it's a phenomenal opportunity to improve their energy efficiency, to eliminate water and chemical use at the hospital, and to actually take those BTUs and reuse them at the campus when we need them in the summer. So there's all kinds of solutions, but it certainly is absolutely critical that the design accommodates the fact that you could be out of balance.
So I'd add a couple things. I think Michael's answer is fantastic. One thing that we're doing at Weber is this idea of charging the deep earth, right? And that's the social science building I've mentioned. Our deep earth temperature is 57 degrees generally. And at that location, we actually get the deep earth up to like 75 or 80 before we go into heating mode. And as we connect more buildings, I'm hoping to drive that a little more. But the one thing I'm working on now that's kind of similar to what Michael was talking about is right next to that basketball arena, we have a hockey rink that's not owned by the university. It's operated by Weber County. But I'm just sitting here thinking, oh, if we could network those, I could harvest heat all the time and dump it into the basketball arena, and everybody would be happy. So looking for those kind of opportunities is very important.
Great. Ted, do you want to add on to anything to that, or are you good?
No, I think I'm good.
Okay. Okay, so the next question is from Stephanie. It says, can anyone speak to the pros and cons of vertical versus horizontal drilling holes, especially when horizontal space is available in sports fields?
I can start with that. I can tell you that for us, the geology in our area and generally in the New England area, there's a lot of available deep bedrock to access. You know, this is generally, there's some glacial till on top of it, but once we get to about like 70 to 100 feet down, we have several hundred feet below that that is competent rock that can be used for geo-exchange. So for us, it's more of a no-brainer to go vertical. But we understand that sometimes there's reasons to go in different directions horizontally. Maybe if you have aquifers that you don't want to tap into, or a lot of kind of water veins that you know are known and are just going to cause more havoc than value in the end. In the end, for us, it ended up being, it's a linear footage question, right? Because in the end, it's just, if you're doing geo-exchanges, how long and how often can you have the piping that where the exchange is happening? How long can you keep it in that state? And so for us, vertical just seems to be the most sense. And talking to our colleagues at other higher ed institutions in our area, we all seem to be coming to the same conclusions.
And I think a lot of it also is sorry to say, it's a little bit of a case by case scenario, because what other work is occurring in the area, and do you take advantage of other construction activity? If you do have the space, there are circumstances where it does make sense to go horizontal. Smith College is an example where they're doing a little bit of both. Carleton College in Northfield, Minnesota also had both vertical and horizontal, and there were reasons for them to do both based on space constraints, based on other construction activities that were occurring at the time. So it really does become case by case, and in a few instances where we've evaluated it, it's come down to almost kind of a horse apiece, and it just based on the preference of the institution.
So I have an interesting situation at one of my satellite campuses. I've got 5 buildings, about 300,000 square feet total, and it's located adjacent to an Air Force base, and there is an underground contamination plume. And the hazmat considerations with drilling into that are not something I really want to deal with. But it is deep enough in theory that horizontal might make sense there as we continue our efforts. But a case by case basis, I think, is valid. And for us, vertical has generally been the approach that makes the most sense.
Great. Thank you all so much. And thanks, Michael, for answering Eric's question in the chat before we closed out. So I just wanted to really quickly bring their contacts, their contact information up on the screen so folks can reach out if they have additional questions, also noting, you know, obviously they are very busy and, you know, just being patient with them if they're not able to respond right away. So thank you again to Michael, Ted, and Justin. We really appreciate all your knowledge that you shared with us. And yeah, any last thoughts between the three of you?
No, it was great. I really appreciated Justin and Ted's thoughts. It was, and thanks, Cammie, for pulling this together. And happy to answer any questions outside of this, folks. Feel free to email me or call me, and I'm sure Ted and Justin would tell you the same.
Yeah, if I see that my email is not on there correctly, so
Oh, I'm
it's
sorry.
it's tmendoza@umass.edu.
I did have one friend go to UMass Amherst, but other than that, I don't know anything about your campus.
I'm happy for you to take all my questions, though, Justin. That's
All right. Well, thank you all so much, and we appreciate it. And everyone have a great rest of your day.
Thanks.
All right. Bye, y'all.